A small habitat stands on the Moon with Earth hanging above it, bright enough to look close, and far enough that nothing out there works by accident. If Mars is the place humans want to reach, why might the Moon be the place where the most important failures need to happen first? The Moon is not Mars. That is exactly why this question matters. It is hostile enough to break real systems, but near enough that a broken seal, a dirty filter, a weak repair routine, or a bad power decision can still become evidence instead of a sentence the crew has to live inside. So the real test is not which world is better. It is where we should discover that our off-world machines are less reliable than their drawings. Soon that becomes the real question. Why the nearest off-world test can matter most when the real destination is far away. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing helps more. Let's begin. Picture a pump alarm inside a sealed habitat. At first it is only a sound at first, a tone, a light, a number sliding out of its usual place on a display. The machine does not know whether it is on the Moon or on Mars. It only knows that something it was supposed to move is no longer moving properly. But distance changes what that alarm means. 3 days from Earth, a failed part can become a repair plan, a redesigned procedure, a new spare, or a hard lesson carried into the next mission. Months away, inside a Mars campaign, the same fault lands in a far less forgiving world. The crew may still solve it, they may be trained for it, but the mission cannot lean on Earth in the same way. This is the first reason the Moon matters in this story, not because it is gentle. The lunar surface is not gentle. It is vacuum, low gravity, radiation and dust. But it is near enough that the first serious failures do not have to be final. We should separate two questions that often get blended together. One is whether humans can survive on Mars. That is the destination question. The other is where we should discover that our survival systems are weaker than we thought. That is the sequence question. And the sequence question may be the colder one. On Earth, engineers expect hardware to fail during testing. That is what a test is for. Pumps leak, valves stick, connectors loosen. Software does something nobody predicted because the physical world is never as obedient as a diagram. The value of the test is not that nothing breaks. The value is that something breaks while the team can still reach it. Mars changes the cost of that discovery. NASA human spaceflight research often frames the Moon as a trip measured in days and a Mars mission as a campaign measured in years. That is not only a travel fact, it changes the moral weight of uncertainty. If a system fails near the Moon, Earth can still take part in the recovery loop. Engineers can inspect the damaged unit after return. Procedures can be rewritten. A later mission can carry a better replacement. A crew can come home with the evidence. None of that is easy, but it is still thinkable. At Mars, the same failure arrives inside a mission that has already committed to distance, delay, and limited rescue. The crew has to carry the consequences longer. The architecture has to absorb them. The schedule cannot simply bend around Earth the way a lunar campaign still can. So the Moon becomes interesting for a reason that sounds almost disappointingly practical. It is close enough for iteration. Iteration sounds boring until you picture what it means. A seal fails in real dust. A filter clogs faster than expected. A crew loses 6 hours every week to a cleaning task nobody counted properly. A spare that looked common on paper turns out to need a tool that is awkward in gloves. A fault tree that felt elegant in simulation becomes messy when tired people have to use it after a long EVA. Each of those failures can look small in a dream about Mars. Each can become mission-shaping if it is discovered too late. The Moon gives those failures a place to appear early. That does not make the Moon a Mars simulator. We should say that plainly now. The Moon has no atmosphere. Mars has one, thin but real. Lunar dust is not Martian dust. Lunar gravity is 1/6 of Earth's. Mars is closer to 3/8. A lunar success does not certify a Mars system, but a test does not need to copy the final environment perfectly. It needs to expose the classes of weakness that would otherwise stay hidden. Here is the personal scale of it. If your water filter at home clogs, the problem is annoying. If a similar kind of clog happens in a sealed habitat where every liter matters, the failure becomes part of survival. Distance decides how quickly help can arrive and how much room the crew has to learn. That is why the word may matters here. The moon may be the test humans cannot skip because it can turn hidden weakness into a visible, recoverable event. It lets a crew fail close to home in ways that would be far less forgiving on Mars. And there is another reason this distance matters. Nearness can preserve evidence. A failed part can be brought back. A scratched seal can be examined under a microscope. A procedure can be reconstructed with timestamps, tools, and crew memory still intact. On Mars, the same failure may be fixed well enough to survive, but the evidence itself can be harder to preserve and slower to interpret. So the test is not only whether something can be repaired, the deeper question is whether the failure can teach fast enough to change the next design. Imagine the crew on the third recurrence of the same warning light. Nobody panics. Calm is good, but nobody should shrug either. Repetition is the data. The moon gives a place for that pattern to appear, while engineers can still change the hardware before a Mars departure locks the design in place. Now the distance test becomes a judgment test. Which faults deserve immediate abort rules? Which ones need a different spare? Which ones need clearer training? Which ones expose a whole architecture that asks too much from tired people in suits? The moon cannot answer every Mars question, but it can force those categories into the open, and it can also reveal a second danger. Nearness can make teams too relaxed. If every lunar failure is softened by the assumption that Earth will rescue the schedule, then the test stops telling the truth. A real proving ground would have to reduce that comfort on purpose. It would have to ask how the crew behaves when help exists, but cannot solve every problem for them. That is where distance becomes more than geography. It becomes discipline. We learn how far support can be reduced before safety begins to fray. We learn which decisions belong on board. We learn which forms of help make the crew stronger and which only hide a weak design. Look at the logbook after the alarm is over. The useful line may not say repaired. It may say the crew spent 20 minutes deciding what evidence to preserve before touching the part. That delay is not waste. It is the difference between fixing a symptom and understanding a fault. The moon gives that logbook a place to grow. One mission can inherit the awkward truths of the last one. A drawer moves, a label changes, a connector becomes harder to misread. The distance test improves because the failure did not disappear into success language. Mars would compress that learning. A crew can still write careful notes there, but the design cannot be changed before the same mission has to keep living with the result. The feedback loop is longer, and long loops let bad assumptions travel farther, so the moon's closeness is not comfort alone. It is a way to make engineering memory faster. We can let the base be wrong in recoverable ways, then force the next version to answer what the surface revealed. The final distance question is not whether a part can be fixed, it is how much uncertainty remains after the fix. A restored system is not the same as an understood system. If people keep glancing at the same panel because nobody knows why the fault happened, then the habitat has not fully recovered. The moon can turn that unease into a design problem before Mars turns it into a long companion. So this is the first standard we carry forward. We are not asking for certainty, we are asking for earlier, cleaner failure while Earth can still help close the loop. And once we accept that, the first system to examine is the one that quietly makes a habitat livable at all. One more reason distance belongs at the beginning is simple. Distance changes how much uncertainty a mission can honestly carry. Near Earth, a team can tolerate a few open questions because the next flight, the next cargo shipment, or the next return path can close them. Farther away, open questions become passengers. They travel with the crew. That does not mean every lunar test must be harsh for the sake of being harsh. It means the test has to be designed to find the right kinds of weakness. A lunar base that only proves the easy parts will not help Mars much. The valuable test is the one that asks what happens when a plan meets the surface repeatedly, when a repair consumes the afternoon, when the ground team has advice but the crew has to choose. A short communication path can hide that if we let it. The Moon is near enough for Earth to speak quickly, and that is useful. But a Mars rehearsal also has to practice the moment when Earth becomes slower, less commanding, and less able to rescue the day. So the Moon's nearness should not be used to remove autonomy from the test. It should be used to make autonomy safer to learn. Think of a crew deliberately given more room to diagnose a fault before calling for a detailed answer. They are not abandoned, they are practicing the shape of a distant mission while the consequences are still recoverable. The point is not to imitate Mars' delay perfectly. The point is to find out which decisions the crew can carry, which ones need better tools, and which ones should never depend on live Earth advice in the first place. A good test plan would so separate failure from catastrophe. It would let crews encounter real broken machinery without pretending the Moon is safe in any ordinary sense. The environment still punishes carelessness. Vacuum still gives no margin. Dust still enters whatever weakness it can find. But the mission architecture can be arranged so that discovery does not automatically become abandonment. That is a rare combination in human spaceflight. Real hostility with a shorter path back to analysis. We should not waste it by asking only whether flags can be planted or milestones can be met. The better question is what the surface teaches when it is allowed to be difficult. The useful question is simple. What would change before anyone takes the same assumption farther away? If the answer is a better procedure, a stronger spare, a clearer display, or a more honest estimate of crew time, then the test has worked. The Moon earns its role when awkward discoveries make the Mars plan less naive. The Moon does not answer the Mars question for us. It only gives us a place to ask it with fewer illusions, better evidence, and one more chance to correct what breaks before distance turns that weakness into commitment. Now picture the habitat after everyone has gone quiet for the night. The air feels ordinary. That is the illusion every good life support system tries to create. Oxygen arrives without being noticed. Water can be poured without the crew thinking about recovery loops and purification stages. Pressure holds, temperature stays within a narrow band. Waste moves into a system that knows what to do with it. A good habitat hides its own effort, but it is not a room. It is a machine pretending to be a room. NASA's life support material makes that clear. Air management, oxygen supply, carbon dioxide removal, pressure control, water recovery, waste handling, ventilation, fire protection, and environmental monitoring belong to the same basic problem. The International Space Station has already proved that important loops can work in orbit. Water recovery on station has reached very high recycling levels. Oxygen can be produced by splitting water. Carbon dioxide can be processed with hydrogen to make water and methane. That is real progress. But Mars does not ask only whether a loop can work. It asks whether the loop can keep working when a crew cannot expect easy resupply, easy evacuation, or constant live support from Earth. Let's follow one quiet failure. A water processor begins to foul. At first the shift is small. A reading drifts, a filter has to be changed a little early. Then another. A sensor reports something odd, but the crew is not yet sure whether the water is changing or the sensor is. Cleaning takes longer than expected. A spare gets used sooner than planned. The habitat still has water, but the system has started taking time from everything else. The Moon is good at exposing that kind of failure. At first it is not cinematic. It does not look like the disasters people imagine when they think about danger in space. What follows is a slow loss of margin. A system that technically works begins to demand more maintenance, more spares, more diagnosis, and more crew attention than the mission plan allowed. Slow failures may be the most Mars-relevant ones of all, because they hide inside routine. A pump that dies loudly is obvious. A recycling loop that becomes needy over months can quietly rewrite the mission. The moon is useful here because surface operations change the life support environment. A lunar crew would bring dust toward the habitat. They would use airlocks and cycle suits. They would live with different thermal rhythms, radiation procedures, power constraints, and repair tasks in a place where stepping outside the machine is never casual. The loop is not being tested as a clean box on a bench. It is being tested as part of a working base. That is what makes the habitat machine honest. Near Earth, we can measure things that drawings often hide. How many hours per week does the crew spend keeping the air and water safe? Which parts foul first? Which valves are easy to reach in principle and awkward to reach in practice? Which maintenance tasks are simple until they are done after bad sleep and a long EVA? NASA's broader human research work also treats hostile and closed environments as one of the central hazards of human spaceflight. This matters because a habitat is not only chemistry and hardware. Temperature, pressure, lighting, noise, microbes, and contaminants shape daily life. A system can keep people alive and still become difficult to live with. So the lunar test is not only can the machine run, it is can people live with the machine while repairing it. That question matters in small ways. It matters when the crew tries to sleep beside fans and pumps. It matters when a panel has to be opened in a cramped space. It matters when a smell appears that nobody expected, or when a filter change becomes a weekly ritual instead of a monthly one. The Mars-relevant burden is not only failure, it is chronic maintenance. The transfer to Mars is strong at the category level. Air monitoring transfers, water recovery discipline transfers, microbial control transfers, redundancy logic transfers, spare planning, repair procedures, and crew autonomy all transfers. But the details do not copy cleanly. Mars has a different outside atmosphere, different gravity, different dust, longer mission duration, and far longer communication delay. That boundary keeps the argument from turning lazy. The moon cannot prove a Mars habitat will work. What it can do is reveal whether a closed habitat becomes fragile when real surface life touches it. It can show which subsystems start consuming crew time, which maintenance plans are fantasy, and which invisible burdens grow with use. Think about the simplest version of that burden. A crew sits down to breakfast. A packet is opened. Moist air moves through a vent. A sample bottle is filled. Somewhere behind a panel, pumps and separators are quietly keeping the ordinary world alive. Nothing feels dramatic, and that is exactly why the test matters. Quiet systems can still be dishonest systems. The numbers can look acceptable while the schedule tells a different story. Recheck this sensor, replace that filter early, clean that line again, wipe condensation, swap another cartridge. None of those tasks sound fatal on its own. Together they decide how much human attention survival is really costing. The moon can make that cost visible in a real routine. After an EVA day, dust reaches the threshold. After exercise, humidity shifts. After a repair, one loop is disturbed while another keeps the habitat stable. We need to know whether life support absorbs those ordinary insults or begins to demand constant nursing. Station heritage matters here, and so does its limit. The ISS has taught engineers a great deal about keeping air breathable and water reusable in space. That evidence should not be brushed aside. But a lunar surface base is not only another module in a cleaner environment. A lunar base has to face dust, suit cycles, different gravity, and the blunt reality that every maintenance hour comes out of the crew's life. A returned water sample from the moon could matter more than it looks. Inside it may be chemistry, microbes, residue, or evidence that a filter behaved differently under surface operations than it did on Earth. The sample is small. The lesson can be enormous if it changes a Mars design before anyone sleeps inside it. So a good lunar test should ask uncomfortable questions. Can the crew reach the failing part? Can they interpret the warning without a room full of specialists speaking into their headsets? Can they clean the affected line without spreading the problem? Can they restart the loop with confidence instead of hope? And the human side stays in the frame. A habitat can be technically safe and still become exhausting. Noise can flatten sleep. Carbon dioxide can stay inside acceptable limits and still leave people dull. A stubborn smell can make everyone uneasy because nobody fully understands its source. Those are not minor comforts. They shape how well people repair the machine that keeps them alive. That makes the habitat more intimate than most diagrams admit. The air you exhale stays in the system. The water you use comes back through machinery. The surface you touched outside may arrive inside as dust. The habitat is not behind the mission. It is the mission's body. Mars sharpens that lesson. A Mars habitat would have to run longer, farther from supply, with fewer exits and slower help. The Moon cannot prove that future. What it can do is tell us whether the operating philosophy is mature enough to deserve the next risk. So the most valuable result may not be a perfect report. It may be a redesigned filter bay, a better sensor location, a shorter cleaning path, a decision to stop trusting one elegant but fragile loop. The Moon earns its place when the habitat machine comes back less mysterious than it was before. Look at the maintenance board after a month. The surprise may not be one dramatic failure. The surprise may be how many small actions cluster around the same subsystem. That pattern has a voice. The Moon gives us somewhere to hear it before Mars turns it into daily life. And that is the habitat standard we carry forward. Not a machine that survives a demonstration, but one that stays legible to the people living inside it. The important measurement may be less glamorous than oxygen percentage or water recovery rate. It may be interrupt cost. How often does the machine interrupt the crew? How often does a small fault drag attention away from sleep, exercise, science, or repair? How often do people stop trusting a reading because it has cried wolf before? Those patterns are easy to miss in short tests. They need time. A system can behave well for a week and become tiresome after a month. A filter location can feel acceptable until the 10th replacement. A sensor can drift slowly enough that nobody notices the first few steps. Surface life is good at turning small design choices into habits, and habits into risk. A lunar campaign can make those habits visible. The crew can log not only what failed, but what became annoying enough to change behavior. Did people postpone a check because it was hard to reach? Did they leave a task for the next shift because the procedure was too long? Did a recurring smell make people open the wrong panel first? These details may sound too human for an engineering report, but Mars will be lived by humans, not by diagrams. Another materials question sits inside every breath. Plastics, seals, adhesives, electronics, cleaning agents, fabrics, and dust all contribute to the closed environment. Trace contaminants are small by definition, but a closed loop gives small things time to matter. The Moon can show which materials behave differently when the habitat is worked, repaired, warmed, cooled, and contaminated by real surface operations. The same logic applies to fire safety and atmosphere control. A sealed habitat has to know what is in its air, where it is moving, and how quickly danger would spread if something began to burn, leak, or overheat. Those are not separate from comfort. Ventilation patterns, pressure zones, filters, and alarm thresholds shape how the crew reads the room. The Moon can test whether the habitat speaks clearly. A warning that is technically accurate but hard to interpret is not good enough. A system that knows something is wrong but cannot help the crew act quickly has not done the human part of life support. Mars will need machines that explain themselves under stress. So the report from a lunar base should not read like a victory speech. It should read like a workshop notebook. What surprised us, what took too long, what wore down, what confused the crew, what needs to be simpler before distance removes the easy repair loop. Those are the lines Mars needs most. Now look down at the boot print. It sits in grey soil under a sky with no weather in it. From a distance the surface can look soft, almost quiet, but lunar regolith is not the dust people know from a shelf or a road. It has not been rounded by water and wind. NASA describes it as sharp, clingy, and operationally hazardous. The particles can stick, scratch, abrade, contaminate, and travel into places the mission would rather keep clean. That sounds like a surface problem. At first it is really a systems problem. Dust is where separate machines begin to touch each other. It rides on suits into airlocks. It grinds at joints and bearings. It reaches seals, tools, visors, filters, radiators, rover mechanisms, power hardware, cabin surfaces, and human skin. It changes how often equipment must be cleaned. It changes how much time the crew spends on maintenance. It can also threaten lungs, eyes, and the ordinary comfort that keeps people mentally sharp. This is why the moon is such a useful proving ground. It has real non-Earth dust close to home. Picture one EVA day. A crew member leaves the habitat and works near a rover. They kneel, they lift gear, they handle tools, they walk back tired, enter the airlock and start the ordinary ritual of getting the surface under control. No emergency has happened, but dust has come back too. Some is visible, some is not. Some stays on the suit, some reaches a seal, some settles somewhere the habitat design did not expect. One EVA is manageable. The 20th is the question. Mars' surface life will depend on repeated crossings between habitat and surface. Every crossing is a new chance for dust to move from the outside world into the air and water world. Every crossing asks the same small questions. Did the cleaning procedure work? Did the suit joint lose margin? Did the filter load faster? Did a latch begin to scrape? Did the crew skip a step because they were tired? Did the maintenance plan count the minutes honestly? The moon can make those questions visible. Mars dust is different. We should keep saying that. Mars has a thin atmosphere. It has wind, it has storms. Its dust has different chemistry and moves under different rules. A lunar dust fix is not automatically a Martian dust fix, but the operating lesson transfers strongly. Dust should be treated as a system-wide contaminant, not a housekeeping nuisance. That change in attitude matters because dust rarely stays in one category. It is a suit problem and a seal problem, a filter problem and a health problem, a radiator problem and a crew time problem. It is also a psychological problem, because contamination that feels impossible to fully control can make the habitat feel less safe even before anything breaks. NASA's regolith hazard work points toward exactly this kind of cross-system burden. Dust can cling electrostatically. It can irritate lungs. It can damage spacesuit boots and sample container seals. It can clog mechanisms and contribute to overheating or malfunction if it coats equipment. The point is not that one particle is dramatic. The point is that repeated exposure turns the whole base into a contamination story. That is why a proving ground moon base should not measure only whether hardware survives a single outing. It should ask what happens after weeks of dusty ingress and egress, which part starts wearing first, which cleaning method sounds good but consumes too much time, which filter geometry is fine on paper and miserable in practice, which cabin surfaces become impossible to keep under control. The transfer to Mars is not perfect, but it is operationally rich. A lunar campaign can teach contamination discipline. It can teach what kind of seals fail early, what kind of airlock routine people can follow when they are tired, what kinds of suit surfaces invite dust to travel, and how much maintenance budget dust quietly steals from everything else. Here is the personal scale of that lesson. Imagine reaching for a tool inside the habitat and finding fine grit where there should be none. The tool still works, but now every hand motion carries a little less trust. If the crew has to wonder where else the dust went, the problem has already escaped the suit. Dust also changes the meaning of design elegance. A mechanism that looks beautiful in a render can become a liability if it has too many delicate edges, exposed tracks, or hidden pockets for abrasive particles. The moon is where those aesthetic decisions become practical ones, and it makes another truth harder to ignore. Cleaning itself is not neutral. Every minute spent removing dust from seals, airlock surfaces, filters, visors, or interfaces is a minute not spent on science, construction, exercise, or sleep. A dust problem becomes a schedule problem long before it becomes a catastrophic failure. That matters for Mars because Mars is farther away at the moment maintenance begins to accumulate. A crew living on Mars could tolerate some contamination if the burden stays low and predictable. What Mars cannot easily tolerate is a contamination regime that quietly multiplies repairs, clogs systems, and drains crew attention over months. The Moon can pressure that assumption early. It can also expose a failure of naming. When people call dust a nuisance, they shrink it to scale. When dust begins to touch life support, power, mobility, and health at once, the word nuisance becomes misleading. The grains are small, the system they interfere with is not. Imagine a habitat threshold after weeks of use. Scuffs mark where boots have crossed. A brush has worn down. A latch is a little stiffer than it was. A filter housing has been opened more times than the original maintenance estimate expected. Nothing in that scene looks heroic, and yet the whole Mars question is inside it. Can the mission live with this burden? Can the hardware tolerate it? Can the crew keep it from spreading into other loops? A useful lunar dust test does not need to solve Martian dust chemistry. It only needs to reveal whether the architecture underestimates contamination as a way of life. The Moon also gives engineers something precious: repetition under real conditions. Not a single sample brought back in a box, but many cycles of exposure, cleaning, inspection, failure, redesign, and return. Dust stops being a chapter in a report there and becomes an engineering memory. And once dust has crossed the threshold, another question follows immediately. Even if the habitat can breathe and the airlock can cope, where do the crew go when the deeper hazard is not contamination but radiation? A dust test also has to be honest about thresholds. How clean is clean enough? A habitat cannot demand Earth-like cleanliness from a world made of abrasive powder, but it also cannot allow contamination to become normal simply because total cleanliness is impossible. Somewhere between those extremes is an operational standard the crew can actually maintain. The Moon can help find that standard. It can show which surfaces need to reject dust, which ones need to tolerate it, which ones need to be isolated, and which ones should never be exposed at all. That sounds like housekeeping until the same dust reaches a radiator, a seal, or an air handling path. Then the standard becomes part of system design. It can also test whether procedures survive human impatience. A cleaning sequence that takes too long will be shortened by reality. A brush that is hard to store will not always be where the checklist assumes. A suit port that saves cabin air may introduce a different maintenance problem. The point is not to blame crews for adapting. The point is to design procedures that can survive being used by tired people at the end of real work. Dust is such a powerful proving ground subject for that reason. It is not one failure, it is a pressure applied everywhere at once. If the architecture can keep dust from quietly linking unrelated systems, it has learned something Mars will need. If it cannot, the Moon lets us find that out before the contamination story has traveled hundreds of millions of kilometers. Dust also tests the difference between prevention and recovery. Some particles should be kept out, some will get in anyway. A mature base has to know both stories. It needs barriers, but it also needs inspection, removal, tolerance, and graceful failure when barriers are imperfect. That is a deeply Mars-relevant habit. No distant base can depend on perfect exclusion from its environment. It has to assume the outside world will find weak paths inward, then design so those paths are visible, limited, and repairable. The Moon lets us practice that humility in a place close enough to learn from the mistakes. The pattern matters more than the isolated incident. One dusty seal can be explained away. 5 related maintenance notes point to an architecture that has not yet admitted how the surface behaves. A nearby proving ground gives engineers time to see the pattern while it is still cheap enough to change. A useful cruelty lives in that pattern. The dust does not care which subsystem owns the problem. It only follows pathways. A mature base has to think the same way, tracing the grain from boot to seal to filter to schedule. The Moon can train that whole chain thinking before Mars turns contamination into a distant habit. Now imagine a warning arriving while two people are still outside. They are not thinking about radiation in the abstract. They are thinking about distance to the shelter, suit mobility, terrain, dust on the path back, whether a tool can be dropped safely, and how quickly the airlock can turn from routine equipment into part of a survival chain. Radiation stops being a number and becomes architecture here. Space radiation is already one of NASA's central human spaceflight hazards. Curiosity's RAD instrument gave us a direct measurement anchor for conditions on the Martian surface, and those readings helped make the scale of the problem concrete. But a dose number alone does not tell a crew how to live. It does not tell them where to sleep, where to work, how fast to move during an alert, how thick a shelter should be, or how much of the habitat must be arranged around a storm event. That is why the Moon matters here, not because it reproduces Mars exactly, but because it exposes crews and hardware to a surface radiation regime outside Earth's atmosphere and magnetosphere, while still staying close enough for redesign, evacuation, and repeated testing. The Mars-relevant question is operational. Can a crew detect, respond, shelter, sleep, work, and repair around radiation constraints? Can a warning system make sense on a long day? Can a storm shelter be reached quickly from the places where people actually are, not from the places a drawing imagined they would be? A shelter on paper is not yet a shelter in the mission. The first lesson a lunar proving ground could make honest is access. It could show whether shielding layouts interfere with routine operations, whether the fastest path back is realistic in a suit, whether a regolith-covered shelter is easy to enter when tools and samples are already in human hands, whether the alert sequence itself is legible under stress. Radiation also touches other systems immediately. A shelter needs power, it needs air, it needs communication. It may rely on water, storage mass, or regolith placed where it can protect the crew. Those choices affect habitat shape, maintenance access, dust movement, and repair work. Radiation never stays in the radiation chapter for long. That matters because Mars planning often runs the risk of turning radiation into a solved geometry problem too early. Bury the habitat, use water as shielding, build a storm shelter. Those are important ideas, but every one of them has to survive real crew operations. Can people reach the shelter from the rover? Can they get there from an EVA worksite? Can they do it at the end of a day when fatigue has already narrowed their margin? Can they move through a habitat layout that still makes sense once tools, dust, and repairs have cluttered the tidy version? The Moon can pressure those assumptions before Mars makes them permanent. It can also reveal which parts of the shielding plan become maintenance burdens. A design that depends on moving regolith regularly, preserving delicate seals around buried sections, or keeping certain passages perfectly clear, may look good until real operations begin. Then the shelter stops being a static structure and becomes one more system the crew has to maintain. Here is the personal scale. You do not experience radiation as a number on a chart. You experience it as where you are allowed to linger, where you sleep, where you store water, how quickly you react, and whether the shelter feels like a routine part of life, or a distant box you only hope will be enough. That is why a lunar shelter test is useful even with imperfect transferability. Mars has a thin atmosphere and different local geology. Transit radiation remains its own problem. Lunar surface tests cannot solve the cruise to Mars, and they cannot certify the exact Martian dose environment, but they can teach the logic of living inside a radiation-aware base. That logic includes drills. It includes route planning, it includes warning thresholds, it includes where the crew keeps emergency supplies and how fast they can reach them when the day is already going wrong. If those things fail on the Moon, the lesson is severe but recoverable. If the same assumptions fail first on Mars, the cost is larger. The Moon can also help answer a quieter question. How much of the base has to be built around radiation before other systems start to suffer? A shelter that is very safe but impossible to maintain, awkward to enter, or poorly connected to the rest of the habitat may solve one hazard by feeding another. So the test is not only whether a dose can be reduced, It is whether protection can become part of an ordinary off-world routine without making everything else less workable. Picture the crew inside the shelter after the alert. They are waiting, breathing the same recycled air, listening to fans, checking systems, and measuring time differently than they did outside. That scene is not about abstract physics anymore. The scene is really about whether the base was built with the honest expectation that radiation changes daily life. The moon lets us stage that honesty near Earth. It can expose whether the route is too long, the shelter too isolated, the drill too slow, the procedure too dependent on perfect timing, or the habitat layout too optimistic about what people will actually be doing when the warning comes. And it can show how radiation begins to compete with other priorities. If the safest shelter location makes repairs harder, if added shielding mass changes structure or power choices, if the route back fills with dust after repeated EVAs, then radiation is no longer a separate problem. It is part of the whole base. That makes the lunar test valuable even without perfect similarity. The point is not sameness, the point is operational truth. Mars will still ask harder questions, but before we answer those, the moon can tell us whether our shelter ideas remain sound once human routine and engineering friction have had their say. And the moment we ask how a shelter stays alive during an alert, another system steps into view. A base only protects anyone while it still has power. Radiation planning also tests whether the base can live with uncertainty. Solar particle events do not arrange themselves around EVA schedules. Warnings may be imperfect. Forecasts may leave room for judgment. A crew has to know when to stop work, when to shelter, and when the remaining risk is acceptable. Those decisions are technical, but they are also procedural and human. The moon can train that judgment close to Earth. A drill can reveal whether the warning language is too vague, whether the crew knows which tools to leave behind, whether the shelter can support everyone comfortably enough for the required time, and whether the base returns to normal cleanly afterward. A shelter that saves the crew but leaves operations tangled for days has still taught a design lesson. There is a social piece too. During a radiation alert, the crew's world gets smaller. People wait in the same protected volume, with the same noise, the same recycled air, and the same knowledge that outside conditions are setting the pace. If the shelter is physically safe but psychologically punishing, that matters for Mars. The place meant to preserve the crew should not quietly degrade the judgment they need afterward. So a lunar shelter test should measure more than dose reduction. It should measure access, habitability, recovery, and interference with the rest of the base. It should ask whether protection has been woven into daily life or bolted on as an emergency idea that nobody wants to use. Mars will need the first version, not the second. A shelter also competes for volume. Every protected space used for storm safety is space not used in another way, unless the design is clever enough to make it serve more than one purpose. Water storage can become shielding. Supplies can be placed with protection in mind. Sleeping areas can be arranged around the safest geometry. But those choices have to work for daily life, not only for an emergency diagram. The moon can show whether multi-use shielding is practical or merely neat. If the protected area is too cramped, too noisy, too hard to access, or too tangled with stored equipment, the crew will learn that immediately. Mars should not be the first place where that lesson is paid for. This is also where rehearsal becomes protection. A crew that has practiced the shelter route, felt its awkwardness and helped change it, is carrying different knowledge from a crew that only read the procedure. The moon can turn radiation planning from a calculation into a lived, corrected routine. The strongest shelter is sewn not only thick, it is available. The strongest shelter is understood. It is reachable from the places people really work. A lunar campaign can make that difference visible, and that difference is exactly what a crew far from Earth would need when warning time is short. Now picture the base during a long, dark stretch. The lights are still on, but every watt has started to matter. Fans, pumps, heaters, sensors, communications, life support. And emergency reserves are all drawing from the same fragile promise that the power system will keep the habitat alive through conditions that do not care what the schedule said. Power is not a support system here. It is the heartbeat of the base. NASA and the Department of Energy both describe reliable surface power as enabling for long-duration work on the Moon and Mars. That may sound obvious, but the important part is not simply that power must exist. It is that power must remain stable through darkness, dust, thermal swings, equipment wear, and human repair. The Moon is useful because it makes that instability tangible. Lunar nights can last about 2 Earth weeks. Thermal conditions can swing brutally. Dust can settle where it is not wanted. Cables and connectors have to live outside. Storage systems have to age. Crews have to decide which loads survive a problem and which ones are shed. Those are not theoretical power questions, they are survival questions. A good lunar power test would ask things simulations often flatten. What happens to a cable run after repeated operations? How quickly can a crew in suits isolate a fault? Which connectors become contamination traps? Does storage degrade the way planners expected? What fails first when a system has to start cold, stay warm, power life support, and still leave margin for work? This matters for Mars because power is where many independent ambitions collide. People want habitat life support, EVA preparation, science operations, resource processing, communication, computing, heating, cooling, and emergency reserve all at once. A system can look adequate until real operations force those loads into conflict. The Moon can reveal that conflict early, and it can do it in a way that leaves evidence behind. Not only whether the lights stayed on, but which loads had to be sacrificed, which repairs took too long, which failures cascaded, and which pieces of the architecture were too delicate for the environment they had to live in. Power is also a repair problem. A microgrid is not only generation, it is routing, storage, switching, connectors, software, priorities, and access. If a crew cannot repair a distribution fault safely in suits, then the elegance of the original design does not matter much. One of the Moon's best uses appears here. It forces the power system to meet real people in real operations. A line has to be traced, a unit has to be opened, a damaged component has to be bypassed or replaced. The question becomes whether the architecture stays understandable when the crew is tired and the clock is no longer generous. The transfer to Mars is strong in categories: microgrid logic transfers, load prioritization transfers, repair doctrine transfers, autonomy transfers, crew procedures around scarcity transfer. But the surface conditions do not copy cleanly. Mars has a different day length, a thin atmosphere, dust storms, different temperatures, and different solar behavior. So again, the rule is not sameness. The real question is whether the class of failure is being discovered where it can still be studied properly. Here is the personal scale. When power becomes uncertain, every other uncertainty speeds up. Fans become time-limited. Water recovery becomes conditional. Heat becomes local instead of ambient. Shelter becomes a countdown instead of a refuge. A base that loses power does not simply become inconvenient. It begins to lose the conditions that make human presence possible. Emergency load shedding matters for that reason. A good lunar test should reveal whether the base knows what to save first, and whether the crew can carry out that plan under stress. Which systems keep breathing for everyone? Which lights can go dark? Which experiments stop? Which processing lines are sacrificed? Which reserves must never be touched unless the crew has run out of other choices? A base that cannot answer those questions clearly is not only underpowered, it is underprepared. The Moon can also expose hidden optimism in the power plan. A design may assume solar surfaces stay cleaner than they do. A storage system may age faster. A cable path may be harder to inspect. A connector may prove too exposed to dust. A crew procedure may take 10 minutes longer than expected, and that delay may erase the margin the grid thought it had. None of those failures sounds heroic. All of them belong to the kind of knowledge Mars needs before it is carried that far. And the Moon brings another advantage. It lets engineers test a surface power architecture as part of the whole base, instead of as a standalone technology demonstration. A power system that works on its own terms may behave differently when it has to feed life support, heating, resource processing, charging, communications, and habitat routine at the same time. That whole base view matters because power never fails politely. If it stumbles, life support notices. Thermal control notices. Communications notice. Repair work notices. Radiation shelter planning notices. The heartbeat is connected to everything. Imagine the crew tracing a fault during darkness. One person checks a panel, another monitors life support reserve, a third watches temperatures drift. The repair is electrical, but the pressure in the room is biological. Everyone knows the base only stays ordinary while the power chain remains legible. That is what a lunar base can test, not only whether a generator, battery, or reactor operates, whether the whole power logic stays calm under real use. And once a base can keep itself powered, the next temptation is obvious. Use what is already there. Stop carrying every kilogram from Earth. Turn local material into something useful. That is where resource use stops being an inspiring idea and becomes another place where systems may prove weaker than their diagrams. Power also exposes the difference between capacity and confidence. A system can have enough generation on paper and still fail to feel trustworthy if the crew cannot understand its state quickly. Where is the margin? Which storage units are healthy? Which loads are discretionary? Which fault is isolated and which one is spreading? A base needs answers that tired people can read. That readability is a design requirement. It affects displays, labels, procedures, training, and physical layout. If the crew has to interpret a power fault through too many layers of software or too much ground support, then the architecture is not yet independent in the way Mars will require. The Moon can reveal that without making every error permanent. There is also a startup problem. Some of the most demanding moments may happen when the base is waking a system, not when it is cruising, bringing resource processing online, heating cold hardware, charging equipment, preparing EVA systems, and maintaining life support can create peak loads that look different from average demand. The Moon can show whether the base handles those peaks gracefully or whether the schedule has to be rewritten around electrical anxiety. A good power rehearsal would so count the boring details: how often cables are inspected, how often connectors are cleaned, how many workarounds become normal, how long the crew needs to understand a fault, what happens when a repair has to be made outside while the habitat is already conserving energy. Those are the details that decide whether power remains a heartbeat or becomes a constant worry. Another quiet power question follows: what can be turned off without damaging the future? Some loads are easy to shed, others create hidden costs if they are interrupted. A processing line may need controlled shutdown. A thermal system may protect hardware from a temperature it cannot survive. A communication window may matter because a decision is waiting. The Moon can teach a base how to ration without lying to itself. Load shedding is not only a switch, it is a priority map. It tells the crew what the mission values when not everything can be saved at once. Mars will need that map to be simple, practiced, and trusted. The same idea applies to every power margin. The first version of the plan is a promise. The surface decides whether the promise is readable under pressure. If the crew can see the state of the system, understand the trade, and act without waiting for Earth to interpret everything, the base has moved one step closer to Mars discipline. Power planning also has to include the emotional effect of uncertainty. A crew that does not trust the grid will work differently. They will hesitate before starting loads, delay tasks, and spend attention watching margins instead of doing the mission. The Moon can show when a power system is technically alive, but psychologically noisy. Now picture a sample moving into a processor. It may be ice-rich regolith from a cold region. It may be soil carrying oxygen and minerals. It may be material that looks promising on a map. At this stage, the mission seems to have found what it was looking for. A resource exists, but detected is not the same as usable. That is the first discipline a lunar proving ground can teach about in situ resource use, or ISRU. NASA's own overview makes the basic case clearly. Long-duration exploration becomes harder as distance grows, and local products like oxygen, water, and methane become valuable because resupply becomes less practical. NASA also says something just as important. The presence of resources does not settle their accessibility, extractability, processing difficulty, or reliability at human scale. That is where the moon matters. A map can tell us something is there. A machine has to tell us whether a crew can actually use it. The chain is longer than people often imagine. Material has to be identified, excavated, moved, processed, purified, stored, transferred, and finally used. Each step can fail in its own way. Digging can wear equipment faster than expected. Processing can demand too much power. Storage can leak, warm up, or contaminate. Crew time can disappear into maintenance. A resource that looked like a mass saver can become a fragile new burden. The moon is useful because it can expose the difference between a resource story and a resource system. Mars gives us an important contrast here. MOXIE on the Perseverance rover demonstrated small-scale oxygen production from Martian carbon dioxide. That was a real step. NASA described it carefully as a technology demonstration, and also noted that a human-scale version would need much more than a successful instrument run. Full generation, liquefaction, storage, and dependable operation at much larger scale are different questions. That is the right way to think about the moon too. A successful extraction test is not yet a dependable resource architecture. A few grams or a clean demonstration run are not the same as a base relying on output day after day. So a lunar ISRU test should ask uncomfortable things. Does the excavation hardware survive the real soil? Does the processor foul? Does the product stay pure enough? Is the storage chain dependable? How much crew time does the whole process demand? Does the energy cost cancel the mass it was supposed to save? Does the system reduce dependence on Earth, or does it quietly add a new stack of brittle machinery? Those questions transfer well to Mars even when the feedstocks differ. Mars has an atmospheric carbon dioxide path, the Moon does not. Lunar ice and regolith chemistry are different. Thermal conditions differ, but the system's logic transfers strongly. Extraction is not enough, integration is the test. That is one reason the Moon can be so valuable before Mars. It lets engineers discover whether a resource architecture survives contact with dust, power limits, maintenance, storage losses, and ordinary human fatigue while Earth is still close. Here is the personal scale. Imagine a crew counting on locally produced oxygen or water, not as a scientific success, but as part of tomorrow's survival margin. The emotional difference between a demonstration and a dependency is enormous. A system the crew merely hopes will work feels very different from one they trust enough to build the day around. The Moon can help close that gap honestly. It can also expose a familiar kind of engineering optimism. A resource chain that looks simple in block diagrams can become crowded with hidden requirements. Conveyors or drills wear faster. Fine particles enter places they should not. Storage vessels need more monitoring. Transfer lines demand more cleaning. Purity standards are harder to hit than expected. Every extra fix creates another maintenance branch. That is how a resource system reveals its character, not in the first celebratory run, but in the repeating cycle after the novelty is gone. And because the Moon is close, each failure can still become evidence. A returned valve can be dissected, contamination can be analyzed, energy budgets can be compared with reality, crew time can be counted honestly. The next mission can bring the redesign. Mars would not remove the value of those lessons. It would simply make discovering them first much more expensive. A lunar proving ground can also teach something broader about confidence. Resources often create grand claims because they seem to promise independence. But dependence can move rather than vanish. If local production only works when spare parts, high-maintenance machinery, and careful ground support remain constant, then the base is not yet independent. It has just changed the shape of its dependency. That distinction matters for Mars, where dependency chains cannot be hidden by proximity forever. So the moon's role is not to prove that ISRU solves off-world living. The point is to make the chain honest. From dig to product, from product to storage, from storage to use. Every step has to survive dust, power variation, maintenance, and human routine. Imagine a cold sample arriving at a processor beside an unfinished storage tank. The scene is modest. A few kilograms of material, a machine, a crew watching numbers rise or stall. Yet the whole question of off-world confidence is inside it. Not did we find something, can we build a life around it? The answer may still be no for a while. That is fine. The moon is valuable precisely because no is still useful there. And even if a resource chain begins to work, it still has to pass one more blunt test. The people depending on it must keep crossing the most fragile boundary in the mission, the line between habitat and vacuum. ISRU also tests the honesty of accounting. It is easy to celebrate what local production might save at launch. Harder to count is everything the local system asks for in return: power, mass, volume, spare parts, crew time, heat rejection, contamination control, monitoring, storage, and failure recovery. A resource system should be judged by the whole bargain, not only by the product at the end. The moon is a good place to force that accounting because the numbers can be checked against real operations. If extracting a useful amount of water requires too many maintenance hours, that matters. If oxygen production works only when the crew protects a delicate subsystem from dust every day, that matters. If storage losses are higher than expected, the resource is less valuable than the map made it look. This does not make ISRU less important. It makes it more serious. A system that could eventually reduce Earth dependence has to earn that role by surviving the ugly middle steps. The moon can host those middle steps without turning every failure into a Mars crisis. And the most valuable lunar result may be a negative one. A site may be less usable than it looked. A process may be too power-hungry. A machine may require redesign. That is not embarrassment if it happens near Earth. A proving ground is supposed to deliver exactly that kind of truth before a distant mission builds its return plan or survival margin around the wrong assumption. A resource test also has to face variability. The feedstock may not be uniform. One patch of regolith may behave differently from another. Ice may be mixed, buried, contaminated, or harder to handle than the remote measurement suggested. If the processor works only for the easiest material, then the system is not as capable as the word resource makes it sound. The moon can turn that variability into engineering evidence. It can tell us how much scouting is needed before extraction, how flexible processing must be, and how much margin a real base should carry when the ground under it refuses to be average. So the best outcome is not simply a tank filled or a kilogram processed. The result should be a chain whose weak links are named. Where did the dirt fight the machine? Where did storage lose margin? Where did a crew task become too delicate? Naming those weak links near Earth is the whole point. Local resources also change decision-making. Once the base has invested in extraction, it may be tempted to keep feeding the machine because the plan depends on it. A lunar test can reveal whether that commitment is wise, or whether the architecture should remain more conservative before Mars makes the dependency harder to unwind. Now picture a gloved hand on a dusty latch. That single motion holds a surprising amount of the mission inside it. Pressure on one side, vacuum on the other. Dust coming home on the suit. Life support riding on the back, tools in hand, fatigue in the body, procedure in memory. A spacesuit is not clothing. NASA's own work treats it much more honestly than that. A suit is a small spacecraft worn around a human body. It has to provide pressure, oxygen, thermal control, ventilation, contaminant control, mobility, and enough usability that the person inside it can still work, think, kneel, lift, and come back alive. The airlock is not only a door either, it is the boundary where the surface tries to enter the habitat, and the habitat tries to hold itself together. That makes repeated EVA one of the clearest Moon to Mars test categories. Mars surface missions will depend on frequent crossings between shirt sleeves and the outside world. Not one dramatic outing, but many. The Moon can reveal what repeated crossing does to seals, joints, bearings, boots, gloves, filters, procedures, and people. The question is not whether one EVA succeeds. The question is what the 20th one costs. A proving ground lunar base could pressure that cost in ways analogues cannot. Suit mobility has to survive real partial gravity and real task repetition. Portable life support systems have to stay dependable while dust accumulates. Airlock procedures have to work when the crew is tired and the day has already gone wrong. Rescue routines have to make sense when a person cannot help themselves efficiently. This is where a lot of neat engineering language meets blunt reality. A suit can be beautifully designed and still be exhausting to maintain. An airlock can be conceptually elegant and still invite contamination. A rescue procedure can look clear until two tired people try to perform it in awkward terrain. The Moon gives those frictions a place to appear early, and the transfer to Mars is strong. Suit maintainability transfers, EVA choreography transfers, airlock discipline transfers, emergency retrieval logic transfers, crew fatigue management transfers. The exact outside conditions do not. Mars has different gravity, atmosphere, contamination behavior, and thermal patterns, but the operational truth of repeated crossings absolutely does. Here is the personal scale. Every EVA starts with the same quiet wager. The crew believes the suit, the airlock, the procedures, and their own bodies are still trustworthy enough for another trip outside. That trust is not built by one success. It is built by repetition without hidden decay. The Moon is where hidden decay can become visible. A latch gets harder to turn. A boot joint begins to wear. A glove loses dexterity sooner than expected. A visor cleaning routine takes longer. A filter step that looked trivial begins to consume attention at the end of each EVA. None of this sounds like a headline. It is exactly the kind of thing that decides whether surface work remains sustainable. This is also where dust and life support fold back into the same story. A bad airlock routine does not stay in the airlock. It becomes a cabin contamination problem. It becomes a suit maintenance problem. It becomes a crew time problem. It becomes a filter problem. The boundary crossing is where many independent systems admit that they are not independent at all. The Moon can teach that without pretending it has already taught everything. Martian suits may need different pressure approaches, different contamination protections, and different mobility assumptions. But if a lunar campaign cannot make repeated boundary crossing legible, maintainable, and survivable, Mars has little reason to trust the same philosophy farther away. A useful lunar test would also count repair burden honestly. How often do suits need overhaul? Which parts fail first? Which tools matter? Which procedures become bottlenecks? Which tasks are simple in a clean lab and ugly after weeks of use? That kind of evidence is difficult to get from a rendering and essential to get before Mars. Imagine the airlock after a long day, tools laid down, dust where nobody wants it. A tired crew member trying to remember whether the sequence has already been broken by one small improvisation. The whole mission lives inside that moment more than most ground speeches admit, and the rescue case matters just as much, not because we expect constant emergencies, but because the whole architecture has to answer them. Can one person drag or stabilize another in this gravity? Can the route back be followed quickly? Can the airlock be turned around without contaminating the habitat more deeply? Can the suit itself tolerate the rough handling of a real rescue? Those are the kinds of truths the Moon can expose while Earth is still close enough to learn from them properly. The deeper lesson is that boundary crossings are not occasional technical acts. They are the heartbeat of surface work. Science, repair, construction, sampling, inspection, and emergency response all depend on the crew being able to pass between protection and exposure repeatedly without the whole system fraying. That is why the Moon belongs in this story. It lets those repeated crossings become evidence instead of ideology. The suit either remains trustworthy through use or it does not. The airlock either stays under control after weeks of dust and fatigue, or it does not. The procedures either hold together when one step slips, or they do not. Mars will still add harsher conditions, but the Moon can tell us whether the boundary itself is stable enough to deserve that next test. And repeated crossings create their own secondary pressure. Every day outside becomes another day of wear, another opened panel, another used cartridge, another component that now has a shorter life than the spreadsheet predicted. That is how the first base slowly becomes something less romantic and more honest. A repair shop. The airlock also tests whether the base can protect clean and dirty zones without making daily work impossible. If the dirty side expands too far, the habitat begins to lose control. If the clean side is protected by procedures that are too slow, the crew will struggle to sustain them. The useful design is somewhere between purity and practicality. The Moon can help find that line through repeated use. After enough EVA cycles, the airlock stops being a concept and becomes a lived space where people bump elbows, place tools, hurry, hesitate, clean, inspect, and sometimes make small mistakes. Those small mistakes are not noise in the data, they are the data. Suit sizing and mobility belong in the same picture. A suit that protects beautifully but makes ordinary repair too exhausting has shifted risk rather than removing it. A glove that preserves pressure but destroys dexterity may turn simple maintenance into a long, frustrating task. A life support backpack that is reliable but difficult to service may become a hidden schedule tax. Mars will not be kind to hidden taxes. The Moon can make them visible, while the suit can still be redesigned, the airlock rearranged, and the procedure rewritten. That is why repeated boundary crossing is more than an EVA topic. It is a way to test whether the whole base can touch the outside world and come back without slowly contaminating itself, exhausting its people, or wearing out its smallest margins. The boundary also shapes the science. If going outside is too costly, the crew will go less often, stay nearer, or avoid awkward tasks. That changes what can be studied and repaired. A suit or airlock problem so becomes a mission scope problem, not only a safety problem. The Moon can measure that contraction. It can show whether the base truly has access to the surrounding surface, or only to the parts easy enough to reach within the burden of suit preparation, dust control, and recovery. Mars will need surface access to be dependable, not heroic. A boundary that works well becomes almost invisible. People trust the sequence, the hardware, and their own movements. A boundary that works poorly stays mentally loud. It makes every outing feel borrowed. The Moon can tell us which kind of boundary we have built before Mars depends on it. This is why airlock design deserves patience. It is a small room with a large responsibility. If it preserves pressure but leaks dust discipline, it has only partly succeeded. If it protects cleanliness but exhausts the crew, it has shifted the failure somewhere else. Now picture the inside of a drawer. It holds spare seals, cables, filters, tools, labels, and components that all looked manageable back on Earth because each one belonged to a different subsystem. On the surface, they begin to look less separate. Every EVA adds wear somewhere. Every repair reveals another dependency. Every workaround consumes inventory the schedule hoped to preserve. This is one of the most important shifts the Moon can force us to see. The first base is not only a habitat, it is also a repair shop. NASA's Moon to Mars planning language repeatedly circles around maintainability, reuse, interoperability, and increasing independence from Earth. That is useful because it treats maintenance not as backstage work, but as part of the architecture itself. A base that cannot be repaired intelligently is not ready to be far away. The Moon is valuable here because it can turn predicted maintenance into measured maintenance. That distinction matters more than it sounds. Mission plans can estimate how many filters will be used, how often a valve may fail, which connectors are common, how much time diagnostics should take, and whether additive manufacturing or onboard fabrication will reduce dependency. But those are still predictions until real crews begin to live with real wear. the surface changes the truth. Dust reaches mechanisms. Gloves slow fine work. Tight spaces become slower to access. A part that should be simple to replace turns out to require an awkward sequence. A supposedly universal fastener appears in a place that is hard to see. A repair manual that looks clear under office light becomes confusing in a cramped module after a long day. That is where the moon earns its place. It reveals which maintenance assumptions survive contact with real off-world life. And it does so while Earth is still close enough for the evidence to matter quickly. A failed unit can come home. A worn seal can be compared with what was expected. Crew notes can be cross-checked against physical parts. The next mission can bring a modified drawer, a different interface, or a redesigned tool. On Mars, the same discovery may still be made. It will simply arrive later and with less room to respond. This is also where the fantasy of independence can be tested honestly. A base can sound self-sufficient because it has spare parts and some fabrication capability. But if it still relies on rare components, opaque fault trees, or constant ground expertise to diagnose problems, then the independence is shallower than it appears. The Moon can pressure that illusion before Mars inherits it. A useful lunar campaign would ask very direct questions. What is the actual burn rate for spares? Which parts fail more often than expected? Which supposedly common components are not interchangeable in practice? How much crew time vanishes into diagnosis? Does onboard fabrication solve problems or create new ones through calibration, contamination, and material limits? Which systems become silent maintenance traps? Those questions transfer strongly to Mars. The exact environment differs, but the doctrine of repair does not. Spares philosophy transfers, modularity transfers, crew training transfers, fault diagnosis transfers, maintenance scheduling and documentation transfer. The logic of deciding what must be repaired immediately and what can be tolerated for a while also transfers. Here is the personal scale. Imagine opening that drawer after a month and noticing that one family of parts is disappearing faster than anyone expected. The mission has not failed, but the drawer is telling the truth sooner than the headlines will. That is what a good proving ground does. It lets inventory become evidence. There is also a deeper human issue here. Repair work eats time. Crew time is one of the least replaceable resources in any off-world mission. If the habitat, airlock, power system, and mobility hardware all demand more attention than expected, the base has not simply become busy. It has become less capable of doing anything else. Science shrinks, exercise gets squeezed, sleep gets bargained with. Risk accumulates in the spaces where the schedule becomes too optimistic. The Moon can expose that invisible tax. It can also show which systems are maintenance traps by design. A machine may be technically reliable but terrible to service. A panel may open beautifully in a render and badly in a real habitat. A part may be durable until the one failure mode that matters demands removing 3 other things first. These are not minor ergonomic annoyances. They are exactly the kind of hidden friction Mars needs discovered early. And the repair shop logic extends beyond hardware. Manuals matter, labeling matters, diagnostic trees matter, common terminology matters. A crew should not have to invent a language for faults while they are already tired. If the Moon reveals that instructions are too fragile, too verbose, or too Earth-dependent, that is a Mars lesson worth paying attention to. Picture an open panel, a worn returned component, a spare being compared against the old part, and one crew member quietly realizing that the official replacement time never included the time it takes just to make the area usable. That scene tells us more about off-world readiness than any single public milestone. The Moon can produce many scenes like that. That is part of its value, because Mars will eventually ask whether the architecture can live without constant rescue from Earth. The Moon lets us stage a controlled move away from that dependency. Enough autonomy to reveal weakness. Enough proximity that weakness can still be studied instead of simply endured. And the hardest system to maintain is not always hardware. The most irreplaceable component in the base is the crew themselves. If spare parts are consumed too quickly, that is a problem. If bodies are worn down faster than expected, the problem becomes deeper. That is where partial gravity enters the picture. A repair shop also needs culture. The crew has to feel allowed to slow down, preserve evidence, and report awkward truths even when the mission wants momentum. If every repair is treated as an interruption to be hidden, the base will learn less from its own failures. If every fault becomes a public drama, the crew may become cautious in the wrong way. The proving ground has to make repair ordinary without making it invisible. The moon can help build that culture because failures can return as objects. A worn bearing, a cracked fitting, a contaminated filter, or a misused tool can come back to Earth with a story attached. That combination is powerful. Hardware without crew context is incomplete. Crew memory without hardware can be misleading. Together they can change a design. This is where interoperability becomes more than a policy word. If two systems use different connectors for no good reason, the repair shop will notice. If a tool works across many panels, the drawer will notice. If a manual uses different names for the same physical action, the crew will notice. A lunar base can turn those irritations into design pressure before Mars inherits the clutter. And clutter matters. Not visual clutter alone, but cognitive clutter. Too many special cases, too many nearly identical parts, too many exceptions that force a tired crew to remember what should have been designed out. The moon can show whether a system is only technically maintainable or whether it is maintainable by the people who actually have to keep it alive. There is a useful humility in treating the base this way. It stops us imagining maintenance as a failure of exploration and lets us see it as exploration's operating cost. A crew that repairs well is not drifting from the mission, it is preserving the mission's ability to continue. The moon can teach which repairs are noble and which are wasteful. Some repair time reveals good design being used as intended. Some reveals a preventable burden the design should have removed. Mars needs to know the difference before a maintenance culture becomes a permanent tax on every objective. Repair evidence also disciplines ambition. It reminds the mission that complexity has a carrying cost. Every unique part, every special tool, every exception in the manual asks the crew to remember one more thing. The moon can show which complexity earns its place and which complexity should be designed out. The repair shop view also rewards simplicity. A simple part that can be reached, understood, and replaced may be more valuable than a sophisticated part that rarely fails but becomes a crisis when it does. Mars will need elegance, but it will need serviceable elegance more. Now picture someone rising from the floor after months in 1/6 gravity. The motion looks easier than it would on Earth. It may even look graceful at first, but the question is not whether low gravity feels lighter in a moment. The question is what that environment does to a human body over time. Once work, exercise, dust, sleep disruption, and repairs are all part of the same life. This is one of the moon's most limited and most valuable lessons at the same time. NASA treats altered gravity as one of the major hazards of human spaceflight. Muscles, bones, the inner ear, the cardiovascular system, and more have to adapt across orbit, the Moon, Mars, and return to Earth. We have a great deal of experience with microgravity and some direct human experience on the Moon. But long-duration data in true partial gravity remain limited. That makes the Moon important for a very specific reason. It is the nearest place where prolonged human life in real partial gravity can stop being mostly a model. But we need to keep the claim bounded. 1/6 gravity is not 3/8. Lunar results cannot directly predict Mars health outcomes. The Moon does not answer the Mars physiology question completely. What it can do is constrain it. It can tell us whether some gravity is enough to preserve more function than weightlessness does. It can reveal how reduced gravity changes fatigue, gait, balance, exercise burden, injury patterns, and work rhythm over months. It can show whether countermeasures designed around microgravity still make sense when bodies are not fully weightless and not fully loaded either. That matters because the human body is one of the few systems in an off-world base that cannot simply be swapped out. A lunar proving ground could expose questions that matter immediately to Mars. How well can people work after months in 1/6 gravity? How do they handle repeated suit operations? How do they recover from slips or strain? Does the habitat need different exercise logic than orbit? Does partial gravity reduce one set of burdens while amplifying another? What happens when reduced loading meets dust, awkward body position, and physically repetitive repair tasks? Those are not only medical questions, they are operational questions. Imagine climbing a ladder, turning a stiff connector, stabilizing another person, or carrying tools after weeks of work in low gravity. The concern is not simply bone density in the abstract. It is whether the body remains a trustworthy work platform for the mission that depends on it. That is the human-scale reason the Moon matters here. It gives the body a way to become evidence instead of assumption. The transfer to Mars is moderate, not absolute. A real partial gravity data point matters because it narrows the space of ignorance, but it does not finish the map. 1/6 gravity may preserve too little, or it may reveal adaptations that do not scale cleanly to Mars. Either way, the lesson is useful because it stops us pretending that any reduced gravity is automatically good enough. The quiet danger the Moon can pressure lives there. The phrase "some gravity" sounds comforting. It can hide an enormous amount of uncertainty. A proving ground lunar base could also force the physiology question to meet the rest of the base. Exercise systems consume time and power. Recovery depends on sleep and noise. Injury risk connects to suit design and airlock routine. Fatigue changes maintenance performance. Every biological question becomes part of the architecture once people have to live with it. The Moon can make that coupling visible. It can show whether exercise hardware fits into daily life or becomes another burden. Whether vestibular adaptation interacts with surface mobility in surprising ways. Whether repeated kneeling, lifting, and stabilizing in partial gravity produces new patterns of strain. Whether return to Earth becomes its own risk window after months away. Here is the personal scale. Imagine finishing a shift and discovering that the body still feels capable in one direction and subtly less trustworthy in another. You can move quickly across a habitat, but standing up after a long repair leaves you lightheaded. You can work outside, but recovery takes longer than the planners thought. That is not a headline. Mars needs exactly that kind of truth early. The Moon also gives us a chance to be more honest about models. So much of deep space human planning depends on combining microgravity data, short lunar exposure, Earth analogues, bed rest, animal studies, and careful inference. Those are valuable, but they still leave a gap where true long-duration partial gravity should be. The Moon is the nearest place that gap can begin to close. Not close completely. Begin, that is enough to matter. Because if the body behaves differently than expected, the mission design has to change around it. Exercise time changes. Work periods change. Suit schedules change. Rescue assumptions change. Even the meaning of normal fatigue changes. A lunar campaign would not solve all of that, but it could reveal whether current confidence about partial gravity is too loose to carry safely to Mars, and bodies do not operate alone. Every adaptation, every fatigue pattern, every strained recovery happens inside a team. That means the next question is not only what low gravity does to a person, it is what off-world life does to a crew when the machine around them is also demanding attention. Partial gravity also changes how we think about injury. On Earth, a stumble, a strain, or a bad lift happens inside a thick safety net. On the Moon, the same kind of event can affect EVA plans, rescue capacity, suit use, and the workload of every other crew member. A small injury can become a systems problem because the crew is small and the base has little spare human capacity. A lunar base can measure that connection. It can show how often people strain themselves during real maintenance, how quickly they recover, which tasks become awkward in 1/6 gravity, and whether exercise programs protect the abilities the mission actually needs. It can also reveal whether people misjudge motion because low gravity makes some actions easy and others unexpectedly unstable. This matters for Mars because crews there will need bodies that can do more than survive medically. They will need bodies that can work, repair, respond, and come home. If partial gravity preserves some functions but not others, mission design has to know which ones. The Moon cannot give the Martian answer, but it can stop the question from remaining purely theoretical. There is a humility in that. The body is not a subsystem that submits neatly to command. It adapts, it compensates, it surprises. A proving ground close to Earth lets those surprises become measurements, protocols, and better design, instead of late discoveries on the far side of commitment. The Moon can also test how people sleep, move, and recover when gravity is low but not absent. Sleep posture, fluid shifts, exercise loading, suit donning, and ordinary balance may all behave in ways that do not match either Earth or orbit. That in-between quality is exactly why the data matters. A Mars planner does not need the Moon to be a perfect physiological copy. They need it to reduce ignorance. If the Moon shows that 1/6 gravity is surprisingly protective in some areas, that changes the model. If it shows the opposite, that changes the model too. Either result is better than carrying an assumption farther than it deserves. The body's evidence will be subtle. It may appear in gait, recovery time, sleep quality, tool use, or the way people judge their own strength. A careful lunar program would treat those small signals as seriously as hardware telemetry, because Mars will depend on the crew's physical confidence as much as on any machine. The Moon can also test return to Earth consequences after longer surface stays. Coming home is part of the mission, not an afterthought. If bodies adapt in ways that make return difficult, rescue assumptions and post-mission recovery plans have to change before Mars inherits the risk. Now picture the crew around a small table after something has gone wrong. One person is reviewing a fault tree, another is listening to a delayed message from Earth. A medical kit is close at hand, not because anyone is in crisis, but because the whole room knows that closed environments turn ordinary uncertainty into a shared burden. This is where crew psychology stops being a soft topic and becomes part of the operating system. NASA's human research work treats isolation and confinement as major hazards for a reason. Off-world living is not only about hardware surviving, it is about people making good decisions while sleep, stress, distance, workload, and uncertainty keep pressing on the same small team. The Moon is useful here because it is far enough to be truly off-world, and close enough that mission planners can deliberately increase autonomy without making every mistake unrecoverable. That may be its best role in the human domain. A lunar proving ground can ask what happens when ground support is reduced on purpose. How well does the crew diagnose faults together? How do they divide attention between maintenance and science? How much private space do they need? What happens to sleep when noise, dust, and uncertainty pile up? How does conflict change when nobody can simply walk away from the habitat that is keeping everyone alive? Those are not side stories to the engineering. They are the medium the engineering has to pass through. A crew is part of the base in the same way a control system is part of the base. The group interprets warnings, carries procedures, improvises when the diagram breaks, and decides which problem is more dangerous when two arrive at once. That is why the Moon matters. It can expose how human behavior and machine behavior interact before Mars raises the cost of both. A habitability problem can become a maintenance problem. Poor sleep can become a diagnosis problem. A crowded interior can turn one repair into 3 delays because nobody can work around each other efficiently. Limited privacy can change patience. Noise can flatten judgment. Those are not soft edges around a hard engineering core. They are part of what determines whether the engineering remains usable. The transfer to Mars is strong in categories. Crew selection logic transfers. Autonomy habits transfer. Medical protocols transfer. Workload planning transfers. habitat design lessons transfer. But Mars deepens all of it with longer duration, greater delay, and less psychological closeness to Earth. That means the Moon cannot reproduce Mars' isolation perfectly. What it can do is test whether the crew can function well when the mission deliberately withdraws some of the invisible support that Earth usually provides. Imagine a sequence where a repair, a medical concern, and an EVA decision all compete at once. The team has to choose what matters first. They have to do that while tired, perhaps irritated, perhaps carrying private worries they cannot fully resolve. Those moments matter because the base is not run by hardware alone. The system is run by people interpreting hardware under pressure. The Moon gives those moments a place to become evidence. It can show whether crews need clearer diagnostic language, quieter sleep periods, more private space, simpler task handoffs, or better autonomy rules. It can reveal whether the mission asks one small team to carry too much context at once. It can also show which support from Earth is genuinely necessary and which only hides a weak local procedure. That is one of the most useful pre-Mars lessons a lunar campaign could provide. Not only can people cope, which forms of support make them stronger, and which keep them from developing the judgment Mars will demand. Here is the personal scale. Imagine finishing a difficult day in a habitat where every person knows the others too well. Every fan is still audible, and every unresolved issue sleeps in the same small volume of air. The success of the base depends not only on whether the crew remains kind or resilient. It depends on whether the mission was designed with enough room for human friction to stay small. The Moon can reveal when that room is missing. It can also test how crews carry medical ambiguity. A small symptom on Earth can become a routine appointment. On the Moon, it becomes a question about evacuation, workload, and confidence. The body and the mission begin to speak to each other more directly. That is useful evidence for Mars, where the distance between symptom and help grows larger. And because crews are part of the operating system, their habits feed directly into reliability. Do they report minor anomalies early? Do they preserve evidence or hurry to get back to schedule? Do they trust the procedures? Do they feel empowered to slow the mission down when something subtle keeps recurring? A good proving ground makes those habits visible before Mars needs them. That brings us to a final systems question. Even if the habitat can breathe, the suits can cycle, the power can hold, the crew can function, and repairs can be made, there is still one harder test left. Can the whole mission repeat? Autonomy can be practiced badly. If a crew is simply cut off from help, the test becomes theatrical. If Earth solves every hard decision, the test becomes shallow. The useful middle is more demanding. Design the mission so the crew carries real authority, then measure where that authority becomes too heavy, too vague, or too dependent on tools that were not good enough. The Moon is close enough to make that learning humane. Ground teams can observe, debrief, and intervene when safety requires it, while still allowing the crew to develop local judgment. That is very different from pretending the Moon is Mars. It is using nearness to build the kind of decision muscle Mars will need later. Communication habits matter here. Does the crew ask Earth for permission, advice, confirmation, or rescue from ambiguity? Does Earth answer in ways that strengthen onboard judgment or replace it? A lunar proving ground can make those patterns visible. It can show when support is genuinely protective and when it has become a crutch. The same is true for medical uncertainty. A minor symptom can pull attention through the whole habitat. Who decides whether the person rests, works, returns, waits, or uses limited supplies? How much does the crew trust its own medical training? How clearly do protocols handle the grey zone between ordinary discomfort and real danger? Mars will live in that grey zone longer. The Moon can teach us how crews behave there first. The crew also maintains the meaning of normal. In a small habitat, normal can drift. A sound that once triggered concern becomes background. A smell that should be investigated becomes familiar. A recurring warning becomes something people work around. That drift can be dangerous because it changes the crew's sensitivity to weak signals. The Moon can expose normalization before Mars depends on it. Debriefs, returned hardware, and repeated missions can reveal where the crew adapted wisely and where adaptation covered a design problem. A serious proving ground should respect crew adaptation without letting it hide engineering weakness. A crew that functions well is not one that never feels pressure. A good crew system is one whose environment, tools, procedures, and authority keep pressure from turning into confusion. The Moon can test that whole arrangement. It can show whether the team is being supported by the system or quietly compensating for it. Trust inside the crew is also operational. People need to know that a concern can be raised early without being treated as weakness or drama. The Moon can help train that culture, because small concerns are exactly where many system failures first show themselves. Now picture day 47 instead of day 1. The novelty is gone. Checklists have been marked, folded, and marked again. Dust has settled into the corners of routine. A repair note from last week is still attached to a panel because nobody wants to forget what it taught. The mission is no longer proving that it can arrive. It is showing whether it can keep going. That is the real threshold most off-world dreams underestimate. A single successful mission proves very little. It proves that one combination of people, hardware, luck, timing, and conditions held together once. A base becomes trustworthy only when landing, unloading, maintaining, sheltering, cleaning, repairing, sleeping, planning, and working can repeat without the whole system quietly eating itself. This is one of the Moon's strongest roles before Mars. It can test cadence. NASA's Moon-to-Mars planning language often emphasizes gradual build-up and repeated demonstration of technologies and operations. That matters because repetition is where assumptions are forced into the open. A one-off success can hide fragility. Repetition usually cannot. The Moon allows many cycles of learn, fix, repeat. Landings can be compared. Cargo procedures can be changed. Airlock routines can be tightened. Power loads can be measured across real work periods. The crew can discover whether maintenance slowly crowds out science, whether robotics actually save effort, whether reuse is real, and whether emergency drills remain sharp after fatigue becomes normal. This is the difference between an inspiring visit and an operating surface system. Mars will eventually need the second one. That is why a lunar proving ground should not judge itself only by whether one mission looked successful from afar. It should ask whether the mission developed a stable rhythm after dust, wear, and ordinary strain had time to accumulate. How many tasks stayed predictable? How many became chronic surprises? How often did science lose to maintenance? How often did small delays multiply into larger ones? Those are cadence questions. They are also honesty questions. The transfer to Mars is strong. Human-robotic coordination transfers, task planning transfers, logistics cadence transfers, emergency rehearsal transfers, system of systems integration transfers. Mars adds different terrain, atmosphere, seasons, dust storms, and communication delay. But the need for stable rhythm does not weaken with distance. It becomes more important. Here is the personal scale. Imagine reaching the point where a crew can predict the week without becoming complacent. They know how long it takes to clean after EVA. They know which maintenance items really matter. They know how much time science actually has once survival work is done. That kind of rhythm is not glamorous. That rhythm is what makes long missions real. The Moon can test whether that rhythm ever appears, and it can reveal something uncomfortable if it does not. A mission may survive and still fail to mature. If every week remains improvisation, if every repair surprises the schedule, if every new outing reopens the same contamination burden, then the architecture may not be scaling toward a base at all. It may only be repeating heroic recovery. Mars cannot afford to confuse those two things. A proving ground Moon campaign should also ask whether robots and humans actually help each other or simply create more choreography. A robot can reduce human exposure in theory and still demand its own maintenance, control logic, communication time, and rescue procedures in practice. Only repetition reveals whether the partnership lightens the mission or complicates it. The same is true of reuse. Reusable systems sound economically and operationally attractive, but reusability has to survive dust, wear, storage, repair, and real inspection. The moon is close enough to test those claims repeatedly instead of once. Imagine a checklist on day 47 with handwritten notes in the margin. Not because the crew is being sloppy, but because the printed version keeps learning from the surface. That is one of the strongest images of a useful proving ground. The mission is no longer performing confidence, the mission is building it. And that confidence has to be humble. If repeated operations reveal that one subsystem keeps consuming too much time, or one route keeps becoming unsafe, or one class of spare keeps running low, the cadence has done its job. It has shown the base where it is still weak. That is the result we want before Mars, even if it is inconvenient. Because Mars will not only ask whether systems work, it will ask whether they keep working after repetition has stripped the charm away. The moon can strip that charm away closer to home. It can tell us whether the first base is becoming more ordinary in the right way. Not dull, but dependable. Not dramatic, but legible. Not invincible, but honest about what it needs. Once a mission can repeat, the original question looks different. We are no longer asking whether the moon resembles Mars closely enough. We are asking whether the moon can filter out false confidence before Mars inherits it. The final test in this story lives there. Cadence also exposes handoff quality. One crew may learn 100 small tricks that keep the base running. If those tricks stay in memory instead of becoming design, the next crew starts too far back. A lunar campaign can test whether knowledge transfers between missions, not only whether one crew became skillful. That is a Mars lesson hiding inside a moon routine. A sustained off-world program needs institutional memory that survives crew rotation, hardware upgrades, and changing mission goals. It needs logs that are actually useful, procedures that improve without becoming bloated, and training that carries the awkward lessons rather than only the clean ones. The moon can make that visible, because missions can follow each other on a timescale where learning still feels connected. A repair note from one crew can become a changed panel on the next flight. A confusing checklist can be rewritten and tested again. A storage mistake can become a different layout. That feedback loop is one of the strongest arguments for practicing close to Earth. Repetition can also reveal whether the mission is scalable. A base that works only because one crew overperformed is not ready for Mars. A base that requires constant heroics has not matured. The moon can separate robust design from human overcompensation by asking the same systems to work again, with different people under slightly different loads. Repetition is also where cost becomes visible, not only financial cost, but attention cost, fatigue cost, spare part cost, and risk cost. A task that looks acceptable once may become unacceptable when repeated every week. A clever workaround may be a warning sign if it becomes part of normal operations. The moon can catch those accumulating costs, while the program can still decide what to redesign, what to automate, what to simplify, and what to abandon. Mars will not remove those costs. It will only make them harder to pay. Repetition should make some things boring in the best possible way. A reliable routine does not need drama to prove itself. It simply keeps working, leaves evidence when it does not, and teaches the next attempt. That kind of boring is precious before Mars. A cadence test should include failure on purpose, not fake danger, but planned drills that interrupt the rhythm and ask whether the base returns to order cleanly. If every interruption leaves confusion behind, the rhythm was never as strong as it looked. Repetition is also how crews learn what the base is really for. On day 1, everything can feel like a mission objective. By day 47, the base has started to sort tasks into what truly matters, what merely looked impressive, and what should never have been placed on the crew's shoulders. That sorting is precious. It tells planners which ambitions fit inside the survival routine, and which ones depend on pretending the routine is lighter than it is. The moon can perform that sorting near Earth. A science plan can be compared with the maintenance reality that squeezed it. A construction goal can be compared with the dust and power costs it created. A robotics plan can be compared with the time spent keeping the robot useful. Mars needs that kind of brutal arithmetic before the mission is too far away to revise its promises. Now step back and look at the whole base again. The habitat is breathing. The airlock carries dust and routine in both directions. Power holds or stumbles. A processor turns local material into something useful, or proves that it cannot do so reliably yet. Suits cross the boundary over and over. Spares disappear from drawers at whatever rate reality chooses. Bodies adapt imperfectly. Crews learn what autonomy really costs. The schedule either develops rhythm or it does not. This is where the moon stops looking like a stepping stone slogan and starts looking like a filter. We should say the limitation first. The moon is not Mars. The gravity is wrong for that comparison. The dust is different. The atmosphere is absent. The communication problem is different. Transit to Mars remains its own enormous challenge. Surface weather and seasonal behavior are different. Long-duration life at Mars distance is harsher in ways the moon cannot reproduce. That limitation matters. But a test does not need to copy the final world perfectly. It needs to expose the failures that would be most expensive to discover later. That is the strongest case for the moon in this whole argument. Not that it proves Mars will work. Not that it is mandatory by physics. Not that it settles politics. It may matter because it can reveal where our confidence is still too smooth. A lunar proving ground can expose whether a closed habitat quietly consumes too much maintenance. Whether dust turns every system into a contamination chain. Whether shelter ideas still make sense once the crew has to use them. Whether the power system stays legible under real scarcity. Whether resource use becomes dependable or remains a demonstration. Whether suits and airlocks survive repetition. Whether spares, bodies and teams all carry hidden costs the plan was not honest about. That is what a filter does. It removes claims that only looked strong because they had not yet been tested under enough friction. The moon can also filter out a more dangerous illusion, the belief that component success equals operational readiness. A valve can pass, a processor can pass, a suit can pass, a shelter can pass, and still the whole system may fail to live together well. The moon is close enough to make those interactions visible and repeatable. That matters because Mars is not a set of separate technologies. It is a single commitment made of interacting burdens. Here is the personal scale. Imagine living inside a base that technically works, yet always feels one recurrence away from trouble because too many things remain only partly understood. That is the state a proving ground should interrupt. It should turn unease into evidence before the mission that carries the unease has already gone too far. The moon may be the place where that interruption is still affordable. It may be where engineers learn that a repair philosophy is too optimistic, where crews discover that one routine steals more time than expected, where partial gravity feels helpful in one way and untrustworthy in another, where a shelter design is good on paper and awkward in life, where resource systems survive the first celebration and then begin to show their real cost. Those are not arguments against Mars. They are arguments against late discovery. That is why the moon can be more important as a filter than as a destination. Destinations inspire. Filters protect judgment. And Mars may need that protection badly. Because if the wrong assumptions first fail on Mars, the crew has to inherit them far from the place where redesign is fast. If the same assumptions fail on the moon, the result can still be severe, expensive and humbling. But the lesson can move faster than the consequence. That difference is not glamorous. It is exactly why it matters. So the bounded answer is this. The moon may be the test humans cannot skip before Mars because it can expose selected failures close to Earth, where they can still become design truth instead of mission-long companions. It cannot certify Mars. It cannot answer every Mars question. But it can reduce one dangerous kind of ignorance, and that is enough to make the moon look less like a detour and more like a hard, useful filter. A filter is useful partly because it is unforgiving. It does not care which claim was attractive in a presentation. It lets some things pass and catches others. The moon can play that role only if the program is willing to admit what gets caught. Weak maintenance plans, fragile procedures, optimistic crew time budgets, resource chains that are not ready, and autonomy rules that still depend too much on Earth. That honesty is the difference between a proving ground and a performance. A performance needs success language. A proving ground needs clean failure. It needs the ability to say this worked, this did not. This transfers to Mars, this does not. And this remains unknown. The last category may be the most important. Unknown does not mean useless. It means the boundary has been drawn. If the moon tells us exactly where its rehearsal stops, it has already improved the Mars question. It prevents planners from smuggling lunar confidence into places where it does not belong. So the moon's value is double. It can reveal selected failures early, and it can mark the failures it cannot reveal at all. Both forms of knowledge protect Mars. One reduces false confidence. The other prevents false transfer. A serious moon before Mars argument needs both, or it becomes just another slogan. The most honest lunar result might sound mixed for that reason. Some systems will prove stronger than expected. Some will fail in useful ways. Some will transfer to Mars only as general lessons. Some will not transfer at all. A mature program can hold all of those truths at once. The moon becomes weak only when it is oversold. If it is sold as a miniature Mars, it disappoints. If it is treated as a nearby environment for selected classes of failure, it becomes much more powerful. The difference is not presentation, it is scientific discipline. The filter metaphor also protects us from a false choice. We do not have to worship the moon or dismiss it. We can ask exactly what it filters well. Then we can ask what remains beyond its reach. The sober path lies between hype and cynicism. That is why this argument stays away from destiny language. The moon does not make humans worthy of Mars. It makes some forms of ignorance harder to carry forward. That is a more modest claim and a more useful one. A filter also has to be connected to decisions. If a lunar campaign reveals that a system is not ready, the program has to be willing to slow down, redesign, or choose a different path. Otherwise, the moon becomes theater. The test only matters if its results can still change what happens next. Proximity is not only physical here, it is programmatic. The moon sits close enough in the chain that lessons can still reshape Mars hardware, Mars procedures, crew training, cargo assumptions, and risk rules. If the lesson arrives after departure, it may still be true, but it has lost much of its power to protect. The image at the end is not a triumphant colony. It is quieter than that, a small habitat under a black sky. Earth overhead, a returned component on a bench, a checklist with a line crossed out because the surface proved it wrong. That may be the more honest beginning of Mars, not a perfect rehearsal, but a nearby world teaching us where our confidence breaks. And if we are willing to listen to that, the moon becomes more than a place we have already visited. It becomes the nearest test of whether we can learn fast enough before distance makes learning harder. The test does not end with a slogan. It ends with a question good engineers and careful crews can keep asking. What did the nearby world reveal that we would rather not discover for the first time on the distant one? If the answer is specific, physical, and uncomfortable, then the moon has done something no speech about exploration can do. It has made Mars planning more honest. That is the kind of honesty this channel is interested in, not less wonder, better wonder. Wonder that can survive contact with filters, seals, drawers, shelters, warning lights, and tired people doing careful work in a place that will not forgive vague confidence. So when we look back at that small habitat under Earthlight, the important thing is not that it looks close. It is that closeness can be used well or wasted. Used well, it becomes a shorter loop between error and improvement. Wasted, it becomes another place to perform confidence without testing it. The difference is the discipline to let the moon be hard, to let it say no, to let it return scratched parts, awkward procedures, tired crews, and better questions. Only then does the nearest world become useful to the far one. Mars is still the father question. The moon is the nearer test of whether we are asking it carefully enough. And that may be the quietest reason the moon still matters before Mars. Not because it answers everything, but because it can make the next answer less careless. That is enough to make the test worth taking seriously, and worth testing well, before the father silence begins, together. At first the moon looked like the nearer place, and Mars looked like the real destination. That picture is still true, but it means something different now. The moon is not valuable here because it wins a rivalry with Mars. It does not. Mars remains the farther, harder commitment. The moon is valuable because it can take certain kinds of uncertainty and force them to speak earlier. A habitat loop that quietly demands too much maintenance. Dust that turns separate systems into one contamination story. A shelter that works on paper and stalls in routine. Power logic that looks stable until real darkness, wear and repair enter the day. Resource systems that impress in demonstration and struggle in repetition. Suits and airlocks that survive one crossing and begin to fray across 20. Spare part assumptions that fail when the drawer starts emptying faster than expected. A body that adapts in some ways and remains uncertain in others. A crew that needs more room, more clarity, or more autonomy than the first design gave them. None of those things needs Mars in order to become dangerous. What Mars changes is the price of discovering them late. That is the heart of the argument. The moon is not a perfect stand-in for Mars, and it should never be sold that way. The gravity is different, the dust is different, the atmosphere is absent, the communication problem is easier, the transit problem is almost a different universe. If anyone says the moon proves Mars will work, they are asking the wrong thing from the comparison. But if we ask a narrower question, the moon becomes harder to ignore. Where should we first learn that our off-world machines are less graceful than their drawings? Where should we discover that ordinary repair takes longer, that routines accumulate dust, that crew time evaporates into maintenance, that confidence was borrowed from ideal conditions, that one warning light keeps returning because the design still has not admitted what it really is? If those lessons appear on the moon, they are still expensive, they are still serious, but they can come home with the crew, with the hardware, and with the evidence. They can become changed procedures, rewritten diagnostics, redesigned filters, different shelters, better labeling, cleaner routes, tougher suits, more honest spare lists. If the same lessons first arrive on Mars, they do not stop being lessons. They simply stop being cheap ones. And that may be the most important thing the moon can offer before Mars. Not certainty, not symbolic progress, not even a guaranteed pathway. Just a place where false confidence has less room to hide. So the honest answer is not that humans must go to the moon before Mars in every imaginable future. The honest answer is narrower and in some ways more demanding. The moon may be the test we cannot responsibly skip if we want the first deep off-world failures to happen where they can still be turned into design truth. That is what makes the moon feel different after this question. It is no longer only the nearest world, it becomes the nearest place where a future Mars mission can be made less naive. And once that is clear, the next question changes too. If the moon can filter out some of our false confidence, then what still remains unsolved on Mars even after the best lunar rehearsal ends? What parts of the distant world refuse to be practiced close to home? That may be the real Mars question. That is a quieter answer than the old exploration slogans, but it is a stronger one. The moon does not have to be the final dream to be necessary to the dream's honesty. It can be the place where the dream is asked to survive pumps, dust, tired hands, bad fittings, awkward shelters, and the slow arithmetic of repeated days.